Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 4.2 and looking at real characteristic roots and damped harmonic motion. In Chapter 4.2, we will continue to examine solutions of linear second-order homogeneous differential equations with constant coefficients. When the roots of the characteristic equation are real, we can relate solutions of the DE to damped spring mass systems and LRC circuits. To begin, recall a linear second-order homogeneous differential equation is of the form here. However, in terms of a spring mass system, we use the following coefficients in the dot notation, where m represents the mass of the system, b the damping coefficient, and k the spring constant. Also recall, when derivatives are explicitly with respect to time, engineers use the dot notation, so that x double dot represents your second derivative, x dot is your first derivative. Here, I will work with the linear second-order homogeneous DE in terms of y's to be really general, though. Finding solutions to the linear second-order homogeneous DE. Using our experience with first-order linear DEs of the form y prime minus ry equals 0, which had solutions of the form e to the RT, we guess this could also be a solution to the linear second-order DE. To verify this, we evaluate the proposed solution in the DE. So let's replace the y in our differential equation with our proposed solution e to the RT. And let's take our derivatives. The way I work this is from right to left. So e to the RT, that's just e to the RT, so I don't need to have the parentheses here. I'll eliminate the parentheses. The middle term, we know that the first derivative of e to the RT is e to the RT times by the chain rule, the derivative of what's in your exponent, which gives us a factor of r. Plus then our second derivative. If the first derivative gave us one factor of r, then the second derivative will give us two factors of r, so r squared e to the RT, which I'll write without parentheses as a r squared e to the RT br e to the RT plus c e to the RT equals 0. We would like to find solutions of this equation. Notice that all three of these terms have a common factor of e to the RT, which we can factor out. Leaving the AR squared plus BR plus C equals 0. Recall, e to the RT, an exponential function, is never 0. Graphically, you probably remember e to the RT can have a graph that's of one of two typical forms. It's either going to be an increasing exponential function if r is greater than 0, and a decreasing exponential function if r is less than 0. But either way, these graphs have a horizontal asymptote that is the line y equals 0 that they never touch. So e to the RT is never 0. So then we have the second factor, AR squared plus BR plus C. This is referred to as your characteristic equation. Notice your characteristic equation has the same coefficients as your original differential equation. It is now just written as a quadratic in terms of r. And as a quadratic, solutions can be found by either factoring or the quadratic formula. Here, I'm going to assume that maybe it's not factorable and use the quadratic formula to write the solutions as r equals, we call the quadratic formula as the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Where our author uses delta, which is the discriminant, b squared minus 4ac. Our author uses the discriminant to characterize the different types of solutions that we will see. Although our author explains it this way, in many of the problems you will look like our solutions are factorable. So let's make a note in homework. Use factorization when possible. What we will find is that there are 3 cases to consider. When looking for solutions to your characteristic equations, you could obtain 2 distinct roots. This is referred to as the overdamped case, and it occurs when your discriminant is greater than 0. Because if your discriminant is greater than 0, then you're taking the square root of a positive number here. So you'll have negative b plus a positive number divided by 2a, and negative b minus a positive number divided by 2a, and hence your 2 distinct roots. You could obtain 1 repeated root. This is referred to as your critically damped case. This is going to occur when your discriminant is equal to 0. Because if your discriminant is equal to 0, then you're taking the square root of 0, and then the square root of 0 is 0. So negative b plus 0 and negative b minus 0, they're the same. But you get 1 repeated root. Or you'll get 2 complex roots. This is referred to as the underdamped case. This occurs when your discriminant is less than 0. Of course, if your discriminant is less than 0, then you're taking the square root of a negative number, which leads to complex or imaginary numbers. Now, our author has broke these different cases into 2 chapters. Cases 1 and 2, these are presented in chapter 4.2. The 2 complex roots case, when you have underdamped motion, our author has presented this in chapter 4.3. To start with, though, let's consider the qualitative behavior of these different types of solutions. If both of the characteristic roots are negative, then the spring mass system is said to be overdamped. In this scenario, the spring mass system will approach equilibrium asymptotically. In case 2, we will investigate the critically damped scenario. Here, the spring mass system can approach equilibrium more quickly. In both the overdamped and critically damped scenarios, the spring mass system can possibly pass your equilibrium solution at most 1 time. In case 3, we will investigate the underdamped scenario. This is covered, though, in chapter 4.3. But with the underdamped scenario, we'll see oscillations around your equilibrium. Let's look at case 1 first. If we get 2 distinct roots to the characteristic equation from the quadratic formula or by factoring, let's say that they're going to be R1 and R2. Then we will have 2 linearly independent solutions of the dE of the form y equals e raised to r1 of t and y equals e raised to the r2 of t, which will give a general solution by the superposition principle as y of t as c1e to the r1t plus c2e to the r2t. Remember, the superposition principle says that any constant multiple of a solution is a solution, and the sum of any 2 solutions is a solution. Or in general, any linear combination of solutions. Is also a solution. If we relate this back to chapter 3, then we can also say that a basis for the solution space can be written as e to the r1 of t, e to the r2 of t. A basis for your solution space. So in general, the method that we will use for solving linear second-order differential equations is to write your characteristic equation right off. Find the roots to the characteristic equation. Again, in chapter 4.2, most are factorable. Write the general solution to the DE using the superposition principle. If you're given an IVP, solve for your constants C1 and C2 last. Let us look at an example. Consider a spring mass system with a mass of 2 kilograms that's attached to a spring with a constant of 6 newtons per meter on a table whose friction coefficient is 8 kilograms per second. Let us find the equation of motion for the spring mass system if it is pulled a half a meter to the right and then released from rest. So we'll start by writing our IVP, our initial value problem. Remember, your IVP is your differential equation along with your initial conditions. Now, for a spring mass system, we know that your DE is your mass, so your 2 kilograms times the x double dot, your second derivative, plus your friction coefficient, 8x dot, plus your spring coefficient, 6x, and this is equal to 0. We also have our initial conditions, that x at time 0 is the 0.5 because it's pulled a half a meter to the right. And your first derivative, x dot of 0, this is equal to 0 because your mass is released from rest with no initial velocity. Okay. Now we'll write our characteristic equation. Remember, your characteristic equation has the same coefficients as your original DE, but it ends up being a quadratic in R. So it'll look like 2r squared plus 8r plus 6. So notice that there's no r on this last term. We're only replacing the 2 derivative terms with r's. Now, while we could use the quadratic formula, most of the problems in chapter 4.2 are factorable. So maybe we could factor out a factor of 2 here. And now this is even more factorable as the product of 2 linear factors. That would have to have an r and an r. Now, it may be a while since you've done factoring of quadratics, but remember, you're looking for 2 numbers that multiply to 3, your constant term, and add to 4, your middle term. And so the 2 numbers that multiply to 3 and add to 4 would have to be plus 3 and plus 1. This leads to 2 roots to this characteristic equation. Either r is equal to -3 or r is equal to -1. And this leads to a general solution of x of t c1 e to the -3t plus c2 e to the -t. Now, in your homework, the first, I think, 3 questions ask you to just write your general solution, and that's your stopping point. The next set of problems in your homework ask you to solve the IVP, like this one here. So let us continue. With your initial value problem, you're given initial conditions on your position, and your initial velocity. So to continue, we'll need our velocity function. So let's go find x dot of t now. So here we're taking the derivative of exponential functions. Remember, the constants are in front. We can ignore the constant in terms of the derivative and just take the derivative of the function. And the derivative of e to the negative 3t is e to the negative 3t times by the chain rule, the derivative of this exponent, which would be negative 3. So negative 3c1 e to the negative 3t. And the derivative of e to the negative t is e to the negative t times by the chain rule, the derivative of negative t brings on a negative 1. Now we'll evaluate these both at time 0. So we'll look at x at time 0. And the great thing about exponential functions, when you plug in 0, you have e to the 0, which is 1. So we just get c1 plus c2. Our derivative, x dot of 0. When you plug in 0, this exponential term becomes 1. So we get minus 3c1 minus 1c2. And from our initial conditions, we know the initial position was the 0.5 because it was a half a meter to the right. And the initial velocity was 0. This gives us a 2x2 linear system of equations that you recall we looked at in Chapter 3. Now, you can use a variety of methods for solving this. However, for most of these problems, the elimination method works well. And so if you were to use the elimination method, and add these together, notice that the C2s would cancel. So we would have then negative 2C1, when you add the C1 terms together, equals 0.5. Or dividing by 2, C1 should be negative 0.25. And then I'm going to use our first equation with C1 being negative 0.25. So negative 0.25 plus C2 had to equal 0.5. And so solving for C2, we should get C2 is 0.75. So let's use these as our coefficients in our general solution, so that we can write the solution to the IVP as x of t is equal to C1 e to the negative 3t plus C2 e to the negative t. As the solution to our initial value problem. Okay. Now, we may ask, does the spring mass pass equilibrium? Let's determine that. To determine if this spring passes equilibrium, we're asking if the position is ever equal to 0. And so we're asking, is negative 0.25 e to the negative 3t plus 0.75 e to the negative t, is this ever equal to 0? And there's several different methods you can use for solving this. I'm going to just separate our terms by moving this 0.25 e to the negative 3t to the right-hand side to get rid of that negative term. Again, this is not the only algebraic way to solve this. When we move it over, it becomes positive. What I lost, yeah, that's right, e to the negative 3t now. And to solve for t, let's divide both sides by e to the negative 3t so that this one cancels. And then we'll also divide both sides by 0.75. So that one cancels. Now, using rules of exponents, e to the negative t divided by e to the negative 3t, this will become e to the 2t, and a 0.25 divided by the 0.75 is 1/3. Here, if we wanted to solve for t, we could imagine taking the natural log of both sides and then dividing by 2. So I think t would be 1/2 of the natural log of 1/3. And if you grab your calculator, we have a 0.5 natural log of 1/3, which should be negative 0.55 if we round to 2 decimal places. But notice that it's negative. So the only time this has happened is when time would be considered negative. So we can say that with this problem, the mass never passes equilibrium. This allows us to say graphically what our solution should look like. So remember, our spring mass system started with an initial displacement of 0.5 meters to the right. And then we released it from rest. And we're imagining that this never passes our equilibrium solution. And remember, our equilibrium solution is when your displacement is 0. So here. Also, maybe using the fact that we know from calculus the limit as t goes to infinity of negative 0.25 e to the negative 3t plus 0.75 e to the negative t. So now recall, as t goes to infinity, e to the negative 3t goes to 0. So this whole term goes to 0. E to the negative t goes to 0. So this whole term goes to 0. And so our limit as t goes to infinity is 0, saying that this is asymptotically approaches your equilibrium, but it never passes it. This allows us to say the solution we're looking at starts at the half and asymptotically approaches your equilibrium. Maybe a great analogy to this is if you've seen commercials recently for soft closed kitchen drawers. Those soft closed kitchen drawers don't slam shut, they glide to a close. Okay, let's try another example. Let's solve the IVP given here with these initial conditions. And I'd like to give you a moment to solve this one on your own. It's very similar to our last problem. So if you could pause the video and rework the solution or work the solution for this initial value problem. I'll see you back here in a moment. Okay, let's see how you did. Let's start by writing the characteristic equation. Remember, your characteristic equation is going to have the same coefficients as your original differential equation, but written as a quadratic in the variable r. Which, in this case, again, ends up being factorable. With factors of r plus 4 and r plus 1. And so two solutions would be given by r is equal to negative 4 and r is equal to negative 1. Because both of your r values are negative, this is what tells us we're dealing with overdamped spring mass system. Now we'll write our general solution. Remember, our general solution by the superposition principle is going to be y of t, c1e to the negative 4t plus c2e to the negative t. So our general solution. And as before, we have initial conditions on the position and the velocity functions. So we'll need the derivative to find the solution to our IVP, so y prime of t. So the derivative should be negative 4 c1e to the negative 4t minus c2e to the negative t. When we evaluate these at time 0, y of 0 should always be just your constants, c1 plus c2, and y prime of 0 would be the negative 4 c1 minus c2. And I notice I wrote on the first line c1 plus c1. That should be c1 plus c2. From our initial conditions, we know the initial position is 0.1. So this is a spring mass system that's potentially pulled 0.1 meters to the right. And this one has an initial velocity of -1. So if this were a spring mass system, the way you'd probably be able to visualize this, maybe here's your table attached to a wall, and here's your spring, and here's your mass on the spring. So this would be a spring that's pulled to the right by 0.1 meters. And then it has an initial velocity that's negative. So then the velocity would be saying it's then thrown or pushed. I'm going to say thrown back towards the left again. Okay, now we want to find the solution to this system of linear equations. And again, most of the time it's easiest to use the elimination method. Notice here that if you add your two equations together, the C2s will immediately cancel. So we'll get -3C1 equals, and 0.1 minus 1, I think is going to be -0.9. Which tells us C1 is going to be, what is it, 0.9 divided by 3? Make sure I get this right. It's probably -0.9 divided by -3, but it should be 0.3. So 0.3. And I'll use the first equation with C1 as 0.3. So this should be 0.3 plus C2 has to equal to 0.1. So that C2 is equal to -0.2. Here are the two constants for our initial value problem. So now we can say that the solution to your IVP is going to be y of t 0.3 e to the -4t minus 0.2 e to the -t. And this would be the stopping point for some of the questions in your homework. But I'd like to go a little bit further and ask the question, does it pass equilibrium? In which case we're asking, are there solutions to this equation? So I'm going to choose to move this -0.2 e to the t to the right-hand side, just so I can get rid of the signed number. Again, there are other algebraic ways of solving this equation. And to solve for t, I'm going to divide both sides by e to the -t so that this side will cancel. Similarly, I'll divide both sides by 0.3 so that this side will cancel. Using rules of exponents, e to the -4t divided by e to the -t, I think is e to the negative 3t. Right-hand side, 0.2 divided by 0.3 as a fraction. I think that's just 2/3. And now if we wanted to solve for t, we would take the natural log of both sides. Divide by 3. Divide by negative 3. Multiply by negative 1/3. Grab your calculator, and I think negative 1/3 natural log of 2/3 ends up being approximately 0.135. So our spring mass system does cross equilibrium. And maybe we could have anticipated this as a possibility because we started with initial velocity that was negative that was throwing this spring to the right. And if that velocity was strong enough, then maybe, well, and it did in this case, it threw it past equilibrium, and maybe our spring mass system can then oscillate once. Okay, so now graphically, what does this look like? So let's draw our coordinate system. And we had a spring mass system that started with an initial displacement of a positive 0.1 meters. We found that it does have it crossed equilibrium one time at 0.135, so maybe that's like right here. And we can still evaluate the limit as t goes to infinity of our original solution. So here we could say that the limit as t goes to infinity of 0.3 e to the negative 4t minus 0.2 e to the negative t, where both of these exponentials that have a negative exponent will go to 0, so that this limit is still 0. But it does it while passing that equilibrium one time. So I think that allows me to say that this spring mass system starts with 0.1, that initial velocity pushes it to the right or to the left, it overshoots your equilibrium one time, and then it'll asymptotically approach your equilibrium. It was kind of a rough graph, but I hope you drew yours a little better than mine. Okay, let's try one more. Let's solve this initial value problem. And again, I would ask that you pause the video and work this one on your own. And after you're done, come back and let's check and see if we get the same solution. I'll see you in a moment. Okay, let's see how you did. So again, let's start by writing your characteristic equation. Again, a quadratic in R whose coefficients are the same as the coefficients of your original differential equation. Again, hoping we saw this as being factorable as R minus 3, R, oh not minus 3, I think it's R plus 3, and then R minus 2. Nope, it was R minus 3. Be cautious with your factoring. I think at our level, we make little mistakes sometimes, like I was about to do. I guess what I'm saying is just verify that the two values we picked, -3 and 2, do multiply to -6, and they do add to -1. I think we make, at our level, I see students making silly mistakes sometimes. We'll verify that works. That gives us two values for R. One is positive 3, one is negative 2. Which allow us to now write our general solution as y of t as c1e to the positive 3t plus c2e to the negative t. Again, because of our initial conditions, we're going to need the derivative. So y prime of t. So 3c1e to the 3t minus c2e to the negative t. Of course, you're probably going to now evaluate these at 0. So we'll then have y of 0 would just be the c1 plus c2. Y prime of 0 would be the 3c1 minus c2. And because of our initial conditions, this is 1, this is negative 1. Again, I like using the elimination method here because when we add these together, the C2s immediately cancel. So we get 4C1 I think that's right, 4C1. 4C1 equals, I think that's 0. Wait, I think I just caught a mistake I was writing. This didn't feel right. We said our R2 was negative 2, but I didn't write the negative 2 in my exponent. And I just noticed that here. Our second R was negative 2, which means where our exponent on our second equation shouldn't have been 1. It should have been minus 2t. Okay. And that would have changed our derivative too. I think our derivative then would not have been this. I think our derivative term, our second term in the derivative should be minus 2c2e to the negative 2t. So when we evaluate this at 0, I think this should actually make this be minus 2c2. Okay, I hope you caught that as I was going through my solution. That wasn't working right. Okay, so we still want to use the elimination method, but I think with this one, none of the variables cancel as we're adding them together. So maybe what we need to do first with this is multiply that first equation, and I'm going to choose to multiply it by 2 so I can get the C2s to cancel again. So I think we get 2c1 plus 2c2 equals 2. And 3c1 minus 2c2 equals negative 1. So that now when we add these together, the c2s will cancel, leaving 5c1 equals 1, or that c1 is 1/5. Now remember, when finding our second solution, it doesn't matter which equation we use, so I'm going to use the original first equation right here. And if C1 is a fifth, then we'll have 1/5 plus C2 is equal to 1, which tells us C2 has to be 4/5. And these are the constants we need for our initial value problem, for the solution to our initial value problem. They'll be written as y of t is the 1/5 e to the 3t plus our 4/5 e to the, let's get that right this time, negative 2t as an exponent. And this is the solution to our initial value problem. Again, you probably wanted to double check and see if this ever passes equilibrium. And you probably did this by setting your equation equal to 0. Again, there's different ways you can solve this. I'm going to move this 4/5 e to the negative 2t to the right-hand side of our equation. And now I'm going to choose to divide each side by the e to the negative 2t to get it on the denominator on the left. Divide both sides by the 1/5 to get it on the right. Using rules of exponents, I think the left-hand side becomes e to the 5t. The right-hand side becomes negative 4/5 divided by 1/5, I believe, is negative 4. And then here you want to recognize that e to the 5t is always positive. And so this has no solutions, and our spring mass system would never pass equilibrium. So now we're thinking graphically, what does this look like? So remember, this was a system that was pulled 1 meter to the right. It was given an initial velocity to the left, so it started moving towards equilibrium. It never passes equilibrium, though. Let's also consider the limit. What is the limit as t goes to infinity? So here we're looking at the limit of 1/5 e to the 3t plus 4/5 e to the negative 2t. Here, as time goes forward, e to the negative 2t goes to 0, so this term goes to 0. But our first one did not have a negative exponent. It's a positive exponent, which means this term, as time goes to infinity, so the entire solution goes to infinity. So graphically, what I'm thinking here is even though it was pulled 1 meter to the right and given an initial velocity towards equilibrium, it never passed equilibrium, and our solution still flies away to infinity, I think our solution will look something like this. This will be the solution to our spring mass system. Of course, this probably does not have a realistic application to it, because how can you pull a spring 1 meter to the right, throw it to the left, and then have it bounce off and go to infinity? Well, it doesn't even bounce off. It never even reaches equilibrium. So maybe this particular differential equation did not have an application, or did not make sense in terms of a spring mass system. It doesn't model a real spring mass system. And maybe we could also notice that by the coefficients that were chosen. Notice these coefficients are both negative. This would mean that you have damping that actually adds power to the system, and a spring constant that adds more energy to your system. So both of these are adding energy because of the way they're written with negative coefficients. So this does not apply to the model of a spring mass system. Okay, let's look at one more example, or one more problem. We'll look at case 2, where we only have one repeated root to the characteristic equation. So when the discriminant of the characteristic equation is 0, we get just a single repeated root, negative b over 2a, and a single solution, e to the negative rt, where r is the negative b over 2a here. We can find a second independent solution of the form t e to the rt using a method that is developed in problem 45 of your homework. And so I'm going to leave that derivation out of this video, and I'll let you look at that on your own later. However, this does provide us two linearly independent solutions of the form e to the rt and t e to the rt. And by the superposition principle, our general solution could then be written as y of t c1 e to the rt plus c2 t e to the rt. And again, notice both these have the same exponent, but it's c1 e to the rt and c2 t e to the rt. Now the rest of the problems we look at, the rest of the method that we looked at still applies. And so our solution method is unchanged. Consider a spring mass system with a mass of 1 kilogram attached to a spring with a constant of 9 newtons per meter on a table whose friction coefficient is 6 kilograms per second. Let's find the equation of motion for the spring mass system if it is pulled 0.5 meters to the right and released from rest. Okay, let's start with our IVP. Because our mass is 1 kilogram, we have x double dot plus our damping coefficient, which is 6, so 6x dot plus 9x equals 0. For our initial conditions, the spring mass system is pulled a half a meter to the right. And because it is released from rest, our initial velocity is 0. We can write our characteristic equation r squared plus 6r plus 9 equals 0. And again, this is factorable as r plus 3 times r plus 3. Notice that this gives us a single repeated root. The root -3 appears twice. So we have one repeated root. Of r equals -3. This allows us to write our general solution as x of t. And let's follow the pattern we have for our general solution up here. C1e to the 3t plus C2t e to the 3t. This is our general solution for our spring mass system. Again, because we're given initial conditions on both the position and the velocity, we need our velocity function. Which would be 3c1 e to the 3t. Now with the second one, this is a common mistake that some of us could make. They recognize that this is a product of two functions of t here. T times e to the t. So you must use the product rule when taking your derivative. So here by the product rule, I'm going to put c2t as your first factor and e to the t as your second factor, e to the 3t. So the product rule, it would be derivative of the first c2t is just c2 times the second, plus by the product rule, the derivative of e to the 3t is e to the 3t times by the chain rule, the 3 times your first function, c2t. We want to evaluate both of these at 0 again. When you evaluate your position function at 0, notice that this factor of t in your second part of your solution will make the whole second one be equal to 0. So we just get c1. And when you evaluate your velocity function at 0, this factor of t makes all of this 0. So I think we just get 3c1 plus c2. Or, oh, I lost my negative here too. This was negative, so there's a negative as the exponent on both of these. Which means my derivative was wrong. I think this was supposed to be a negative here. I'll put the negative here. Be careful of those sign errors. I think I had to have a negative here too. Okay. Make sure I don't make any mistakes. So it'd be negative 3c1 plus c2. Now from our initial conditions, we know the initial position is 0.5 and the initial velocity had to be 0. Of course, right away we can see that c1 has to be 0.5. But if c1 is 0.5, then we have negative 3 times 0.5 plus c2 has to equal 0, which I think tells us c2 has to be positive 1.5. this allows us to write our solution to the IVP as x of t 0.5 e to the negative 3t plus 1.5 t e to the negative 3t. There we go. I guess as I've been doing on the other problems again, we might want to ask, does our spring mass system ever cross equilibrium? And this one I'm going to look for my solution a little bit different. I think with our two terms that we have in our solution, both having an e to the negative 3t, I'm going to factor out the e to the negative 3t. Well, I'm going to factor out also the coefficient. Let's factor out 0.5 e to the negative 3t, which will leave 1 plus 3t equals 0. So again, recall that this e to the negative 3t is never 0. So the only way that we're going to get 0 is if this factor is 0, which I think happens if t is equal to negative 1/3. And again, that negative time says our solution never crosses equilibrium. So solutions graphically. And I'm running out of room here, so I'm trying to squeeze this in this little spot. So we had a spring mass system that was pulled 1/2 meter to the right. So this is our starting position. It was released from rest, but the spring's naturally going to pull it back towards equilibrium. And so we now probably want to see what does our solution look like as it moves back towards equilibrium, which means we'll probably want to evaluate this limit again. And so maybe we would want to say, what is the limit as t goes to infinity of the 0.5 e to the negative 3t plus 1.5 t e to the negative 3t. Of course, as t goes to infinity, I can say for sure that this first term, e to the negative 3t, goes to 0. However, for the second one, when t goes to 0, when we plug in t goes to infinity, I think this ends up looking like infinity times 0, which is technically, remember from calculus, an indeterminate form where we would have to apply L'Hopital's rule. And I'm running out of space here to confirm this, but I'm going to ask you to confirm what this limit is using L'Hopital's rule. But what you should be able to confirm is that this limit is still 0. So our spring mass system, starting 1/2 meter from equilibrium, will have a limit that approaches 0, and it might look something like this. Graphically, what we would like to see with a solution like this one, which our author refers to as critically damped, is a spring mass system that still approaches equilibrium, but it does it a little bit more quickly than the other solutions we looked at. Okay, I'm going to stop this video here. I still need to discuss one more idea in chapter 4.2, the RLC circuits, but I'm going to do that in another video. So I'll see you then.